What comes to your mind when I say black holes? Monster, astronomical sized vacuum cleaners that suck everything into them, right? Of all the mysteries in astrophysics, if there's one that tops the list, it's got to be black holes. And why not? At its very center, maths and physics as we know it literally breaks down. Well, before we jump into a black hole, let us understand on how they come into existence, shall we? Based on their mass, black holes can be categorized into four different types. Stellar mass black holes that are formed out of a collapsing star, supermassive black holes that are at the center of almost every galaxy, intermediate mass black holes whose mass is in between that of stellar mass and supermassive black holes, and primordial black holes that are believed to have been formed soon after the Big Bang. There is some speculation that Planet 9 could be a primordial black hole the size of a golf ball. We'll get to that later. Stellar mass black holes are formed when a star 30 or more times the mass of a sun reaches the end of its life. You see, in stars that are smaller than 8 times the mass of our sun, when its nuclear fuel runs out towards the end of its life, the collapse of gravity is held back by a quantum physical force called as the electron degeneracy pressure, where the electrons prevent gravity from squishing them further, and a superdense white dwarf is left behind. This is how a sun will end its life too. In case of stars that are between 8 to 29 times the mass of a sun, this inward push of gravity at the end of its life is held back by a stronger quantum physical force called as the neutron degeneracy pressure, where, as you guessed it, neutrons resist gravity from squishing them further, and an even denser core called as a neutron star is left behind. But when a star more than 30 times the mass of a sun runs out of its nuclear fuel, there's no force that we know of that can halt the inward collapse of matter due to gravity. We think it collapses to a point that has no dimensions, called as the singularity. Singularity is what is at the heart of every black hole. Supermassive black holes, on the other hand, are believed to have formed very early on in the universe, inside the first massive galaxies. In fact, today we see them at the center of almost every galaxy. Last year, we snagged a picture of one feeding at the center of an elliptical galaxy called as M87. Even our Milky Way galaxy has a supermassive black hole at its center, and it is called the Sagittarius A star. It has a mass of 4.3 million times the mass of our sun. All the stars in our galaxy, including our sun, orbit the supermassive black hole. Unlike other supermassive black holes, it is not actively feeding as of now. However, the one at the center of M87 is, and when they do, they put up quite a show. They shine brighter than the entire galaxy itself and can be seen across the universe. In fact, these are few of the most distant objects we have ever detected, stretching all the way to a few 100 million years after the Big Bang. Quasars, acronym for quasi-stellar radio source, as these actively feeding supermassive black holes are also called, play a vital role in the evolution of a galaxy. Intermediate mass black holes have been a bit of a mystery until the recent past. You see, intermediate mass black holes have not been directly observed so far. Their existence was inferred based on indirect measurements, like the velocity of the accreted gas around them. However, on the 21st of May 2019, the LIGO and Virgo gravitational wave observatories witnessed ripples in space-time from the merger of two black holes, one 85 and the other 66 times the mass of our sun. The merger resulted in a black hole that was around 142-ish times the mass of our sun. That puts it in the sweet spot of the elusive intermediate mass black holes. As their name suggests, primordial black holes were born very early on in the universe, a mere fraction of a second after the Big Bang. It was a long time before stars or even galaxies could exist. That's because in that fraction of a second after the universe itself began, space was not completely homogeneous yet. Instead, some areas were denser and hotter than the others, as shown in the cosmic microwave background. And these dense regions could have collapsed into black holes. Primordial black holes could have masses ranging from a tiny speck to 100,000 times the mass of our Sun. Even though we've not observed any primordial black holes directly so far, scientists speculate that the unusual pattern in the orbits of trans-Neptunian objects might be due to a primordial black hole, aka Planet 9. All these black holes vary in masses, but are similar in terms of the effect that they have on their surrounding space. For example, we know that time runs slow and light takes elongated paths around objects that have mass. But this effect is super exaggerated around a black hole, which results in weird phenomena. You see, on the surface of the Earth, the escape velocity is 11.2 kilometers per second. Throw an object faster and it will escape Earth's gravity, considering that it's not slowed down by the friction from air. Imagine you could somehow compress the Earth while keeping its mass the same. As you do this, the escape velocity at the surface of the Earth keeps increasing until we reach a radius of 1 inch. You could squeeze the entire mass of the Earth into a sphere the size of a basketball and still not have a black hole. The light emitted from that mass can still escape the intense gravitational pull. However, if you squeeze the mass of the Earth into a sphere the size of a ping pong ball, it becomes a black hole. At this radius, the escape velocity at the surface of the Earth becomes equal to the speed of light. The radius at which the escape velocity at the surface of any object becomes equal to the speed of light is known as the Schwarzschild radius. Every object has a Schwarzschild radius, which can be calculated using this equation. And in case you're wondering, yes, we humans also do have a Schwarzschild radius, and it is 10 to the power of minus 23 centimeters, much smaller than the nucleus of an atom. Compress a human to that extent and pop, he'll turn into a black hole. Keep this handy next time your parents pressurize you too much. Simply tell them you'll turn into a black hole if they continue to do so. Black holes are theorized to go way past beyond the Schwarzschild radius and collapse to a point of no dimension in case of non-rotating black holes. But most of the black holes observed have a spin associated with them. This comes from the conservation of the angular momentum of the star or the gas cloud that the black hole initially formed from had. Since a point cannot support rotational or angular momentum in classical physics, the minimal shape that is singularity that can support these properties is instead a ring that has zero thickness but has non-zero radius, and this is referred to as a ringularity or Kerr singularity. To the outside world, black holes appear as black spheres. The surface of the sphere is called as the event horizon, whose radius is equal to the Schwarzschild radius. The space between the surface of the event horizon to the singularity at its center is curved to such an extent that no light can escape. Objects that cross the event horizon can never make it back, as they need to travel even faster than the speed of light beyond this boundary in order to escape the gravitational pull of the black hole. And nothing, not even light, can travel faster than the speed of light. So yeah, they're doomed. But the object itself will remain intact depending upon the mass of the black hole. As the object moves closer to the singularity, the side facing the singularity experiences more gravitational pull when compared to the side facing away and is stretched in a phenomenon known as spaghettification, where the object is nothing but a long string of atoms. That's about it for whatever or whoever falls into a black hole. Things get more interesting when a black hole is surrounded by a swirling disk of glowing gas called as the accretion disk. The immense gravity of the black hole would deflect the light emitted by this disk to make it look very unusual. Surrounding the event horizon is a thin circular image of the orbiting disk that marks the photon sphere, comprised of photons orbiting the black hole that eventually make their way out after several orbits. The accretion disk that orbits the black hole at fraction of the speed of light appears brighter on one side that is moving towards you when compared to the side that is moving away from you. This is due to Doppler effect. Space is bent so weirdly around a black hole that even the far side of the accretion disk, which should generally be hidden from the view, is also visible. Some actively feeding supermassive black holes create jets of particles and radiation traveling close to the speed of light that sometimes can be as large as the galaxy itself. While some accreted matter falls towards the central black hole, a small fraction of it gets spun out in two narrow beams along the axis of rotation of the black hole. These jets are believed to be the sources of the fastest traveling particles in the universe, known as cosmic rays. In some cases, these jets can result in giant radio lobes far from the galactic center. Centaurus A is one such galaxy where we see this in action. Black holes are indestructible, right? Nope, they aren't. Like everything else, even black holes don't last forever. They lose their energy through a mechanism known as Hawking radiation, where a pair of virtual particles pop in and out of existence due to quantum effects. Anywhere else, these particles pop in and out of existence, borrowing energy from the universe and returning it back in less than a fraction of a second, conserving the total energy of the universe. But when this happens at the event horizon, the photon created inside the event horizon falls inside the black hole, and the photon created outside escapes into the universe. As the energy of the universe needs to be conserved according to the law of conservation of energy, the black hole ends up paying for this loss in energy for the creation of this photon, which escapes into the universe. Hawking radiation is inversely proportional to the black hole mass. So, micro black holes are predicted to be larger emitters of radiation than the more massive black holes, and thus should shrink and dissipate faster. Black holes are some of the last objects to decay in the universe. After all the stars, white dwarfs, neutron stars are burnt out, even the last of the supermassive black holes will radiate into the universe in about a Google year, which is 1 followed by 100 zeros. After all the black holes have evaporated, once a light-filled and teeming with life universe will be all but empty.